Have you ever wondered what would happen if everything we thought we knew about electric vehicle batteries was only the tip of the iceberg? For decades, the battery war has revolved around one single name: lithium. Companies have poured hundreds of billions of dollars into it, argued over it, worried about its supply, and done everything they could to stretch its lifespan by just a few more percentage points every year. That was the game. That was the race. And almost the entire world accepted those rules. But then, something leaked from behind closed doors in Austin, Texas. Not from a flashy press conference, not from an Elon Musk tweet, but from numbers that, according to internal sources, were never supposed to leave the walls of that high-voltage lab. And when those numbers got out, they did not just shock people, they shook the entire electric vehicle industry down to its foundation. We are talking about a completely new kind of battery, an aluminum-ion battery. No cobalt, no lithium, no supply chain depending on any single country, a range of 550 miles, a charging time of 5 minutes, and performance that does not fade even after tens of thousands of charging cycles. Sounds too good to be true? That is exactly what I thought until I dug into every single detail. So what actually makes this technology different from the hundreds of promises Tesla has made before? Why are major automakers in Detroit, Stuttgart, and Shanghai watching Tesla's every move with nervous eyes? And most importantly, is this the real turning point that will change how we move, or is it just another dramatic reveal that will eventually fade into the background? We are going to break it all down in today's video, layer by layer. Before we get into the story, if you like deep dive videos like this, no clickbait, no exaggeration, hit subscribe and turn on notifications so you do not miss the next episode. Now, let's get started. When lithium is no longer enough. To understand why Tesla's aluminum-ion battery could be a real earthquake for the industry, we need to go back to the beginning and ask one simple question. Why has lithium dominated the battery industry for so many decades? The answer is not complicated. Lithium is the lightest element on the periodic table that can store and release electricity in a stable way. It offers better energy density than lead, nickel-cadmium, or older battery technologies. And when phone companies started needing small but powerful batteries in the 1990s, lithium-ion became the default standard. When electric vehicles began taking off in the 2010s, lithium was carried straight over. Nobody questioned it. Nobody seriously proposed replacing it. The race was simply about making lithium a little better, a little cheaper, and a little safer. But lithium comes with built-in problems that no one has fully solved. First is thermal runaway. This is the reason lithium batteries can catch fire when they are damaged or overcharged. It is not just a small engineering flaw, it is a basic chemical trait. Once the temperature passes a certain threshold, the reaction starts producing its own heat and becomes impossible to control. Every year, there are hundreds of electric vehicle fires around the world, and this is the main reason. Second is capacity degradation. Lithium batteries gradually lose their ability to store energy after every charging cycle. After 500 full charges, many electric vehicles only have 80 to 85% of their original capacity left. After 1,000 cycles, many cars no longer have the practical range needed for long-distance trips. Third, and this may be the least talked about problem, is geopolitics. Lithium is concentrated mostly in South America, while cobalt, a key ingredient in many lithium batteries, comes largely from Congo, where mining conditions are tied to serious human rights concerns. And refining. More than 80% is controlled by China. This is not just an engineering problem, this is a national strategy problem. And whoever solves it first, not just in a lab, but at a production scale of millions of units, will hold an advantage that money alone cannot buy. But to understand why what Tesla has just done matters so much, we need to look at the heart of the entire story, the new battery itself. Aluminum, the element forgotten for decades. Aluminum is the third most abundant element on Earth. It is everywhere in drink cans, airplane frames, and building structures. It is light, strong, and especially easy to recycle. So why, for decades, has almost no one seriously used it for batteries? The answer comes down to a problem called ion lock. In theory, aluminum can store and release electricity very well, But in practice, aluminum ions cannot move fast enough through the electrode structure to create a stable, rapid flow of electricity. They get trapped. As a result, aluminum-ion batteries in earlier experiments always had slow discharge rates, unstable performance, and quick degradation. Most of the scientific community gave up on this path after decades of failure. Aluminum ion was placed in the category of good ideas that just were not practical. But Tesla did not give up. According to leaked internal sources, Tesla's engineering team in Austin spent years researching a completely different approach, not changing the element itself, but changing how that element behaves inside the battery. The solution they found was a proprietary bonding substrate, a carbon-graphene mixture with atomic-level sensing points. When aluminum ions come into contact with this structure, a phenomenon happens that Tesla engineers internally call quantum burst discharge. Put simply, in a way that is easy to picture, if a traditional lithium battery is like dial-up internet from the year 2000, Tesla's aluminum-ion battery is like high-speed fiber optic internet. The amount of information may be the same, but the transfer speed is on a totally different level. Lab results reportedly showed 7,000 watts per kilogram, a specific power output 5 times higher than Tesla's most advanced 4680 lithium-ion battery. That number is not a normal improvement, it is a generational leap in technology. And there is one more thing, something so counterintuitive that many engineers did not believe it the first time they heard it. This aluminum-ion battery performs better as temperature rises. Lithium batteries start losing performance above 40 degrees Celsius, and at 60 degrees Celsius, the risk of thermal runaway becomes genuinely concerning. But Tesla's aluminum-ion battery reportedly reaches peak performance at 85 degrees Celsius. Where lithium dies, aluminum-ion wakes up. That is not just a technical advantage, it also means complex and expensive cooling systems could be greatly simplified, reducing both cost and weight across the entire system. At first, it sounds simple. Aluminum conducts better when it is hot. But that small detail could change the entire game when you think about a vehicle driving through the Arizona desert in summer or an electric truck pulling a heavy load at high speed for long periods of time. The numbers that were never supposed to leak. Inside Tesla's high-voltage testing room, there were data points reportedly described as never being allowed outside. But they did get out, and what they revealed has reshaped the way we look at the future of electric vehicles. After 10,000 full charging cycles equal to more than 25 years of daily use, the aluminum-ion cells showed no recorded power degradation at all. Not 1%. The same torque, the same launch speed, the same driving range. For comparison, even the best current generation lithium-ion batteries begin showing degradation after 500 to 800 cycles. Tesla is claiming a completely different standard. The battery management system, internally called QBC, or quantum burst control, does not simply regulate electrical current. It shapes the current, adjusting each electrical pulse to the resonant frequency of the battery cells in real time. This is no longer ordinary battery technology. It is closer to advanced system control in the highest technical sense. In simulated urban delivery truck tests, constant hard braking, operation between -10 and +90 degrees Celsius, heavy loads, rapid acceleration, the battery reportedly never thermal throttled once. Not once. That is something most electric vehicle makers still have not solved today. And regenerative braking? The superconductive pathways of aluminum ions reportedly allow up to 98% energy recovery during braking, compared with 70 to 75% for the best current lithium-ion batteries. In dense urban environments like Los Angeles or Chicago, that means around 20% more practical range, not from charging more, but from braking. You are not just stopping the car, you are putting energy back into the battery. Then came the fast-charging demonstration. At a private investor event, Tesla reportedly brought out a Model 2 prototype, plain, undecorated, with no showmanship, plugged it into an existing standard supercharger station, and started the clock. 5 minutes. Not 50, not 30. 5 minutes to reach 80% capacity. The room did not applaud. People sat in silence. Because everyone in that room understood, if this is true, The biggest fear millions of American consumers have about electric vehicles just disappeared. After that, Tesla reportedly revealed internal survey data showing that 65% of American consumers who are hesitant about electric vehicles say charging time is the #1 barrier. That may no longer be a problem. But no matter how impressive a technology is, it means nothing if it cannot be manufactured at scale at a cost regular consumers can actually accept. The factory, the strategy, and the global production machine. This is the part many people overlook when they hear about a new battery technology, and yet this may be the part that decides everything. According to Tesla's rollout plans, Giga Mexico is described as the first production facility designed from the ground up for aluminum-ion batteries not converted from an old lithium production line. That matters because it allows the entire process to be optimized from the beginning. Dry electrode manufacturing completely replaces the traditional wet process. The old method consumes billions of liters of water every year and requires massive factory space to run drying systems. Tesla's new method eliminates that, cuts production time in half, and significantly reduces the factory footprint required. But the truly surprising strategy is not one giant factory. It is a distributed model, a network of micro-factories spread across the world. Each unit could produce up to 1 million battery packs per year, operating independently with AI support that tracks market demand in real time. This is not just a manufacturing issue. It is a geopolitical issue. When batteries are produced in 20 different countries using locally available aluminum, the global supply chain can no longer be controlled by any one country or corporation. And the cost? This is the number that could truly shock the industry. Tesla's projected production cost for aluminum-ion batteries is expected to fall below $40 per kilowatt-hour, compared with $120 per kilowatt-hour for current lithium-ion batteries. That difference is not a marginal improvement. It is the collapse of the old economic model. The direct result, the Model 2, an electric vehicle built around this battery, is reportedly priced under $16,000, a range of 550 miles, 0 to 60 miles per hour in just over 3 seconds, and a charging time of 5 minutes. When test drivers first experienced the Model 2 prototype without knowing what technology the car was using, they described it as if the car could read the driver's intention before the foot even touched the pedal. No delay. No performance drop after repeated acceleration. Just continuous, smooth, uncompromising power. But of course, not everything is bright and easy, and this is where the story gets more complicated. The challenges and unanswered questions. Before we get completely swept up in the excitement, we need to stop and take a more realistic look. First, most of the information about Tesla's aluminum-ion battery comes from internal sources that have not been officially confirmed. Tesla has not held a technical press conference, has not released peer-reviewed data, and has not had any independent third party verify the numbers being quoted. That does not mean the numbers are wrong, but it does mean we are still in unverified territory. Second, Tesla's history is a history of big promises coming before real-world production. The Cybertruck, the Semi, the second-generation Roadster all were promised years before they actually reached the road. Expectations around when people can truly buy a Model 2 for under $16,000 need to be placed in that context. Third, even if aluminum-ion battery technology works perfectly at lab scale, jumping to production of millions of units per year is a totally different challenge. Many promising battery technologies have died at this exact stage. Solid-state batteries have been promised as the next revolution for more than a decade, and they still have not reached mass production at a reasonable cost. Fourth, charging infrastructure. Even if the new battery can charge in 5 minutes, that requires extremely high power transfer, and not every current charging station can support that. Upgrading the global supercharger network to match the charging speed of aluminum-ion batteries would be a massive investment challenge, even for Tesla. And finally, aluminum, while more abundant than lithium, still requires a huge amount of energy to refine. A geographic supply advantage does not automatically become a cost or carbon emissions advantage if the refining process still depends on fossil fuels. These questions do not erase the technology's potential, but they remind us that the road from a lab breakthrough to a product in the hands of everyday consumers is always longer and harder than what is shown in polished PowerPoint slides. And this is where the race becomes even more intense, because Tesla is not the only company trying to dominate the future of electric vehicle batteries. Who is chasing Tesla? The global competitive picture. Tesla is not fighting alone, and that is what makes this story even more interesting. China, through BYD, is currently the world's largest electric vehicle maker by volume. BYD is selling the Dolphin for around $13,000 in many markets. But BYD's battery is still lithium iron phosphate, efficient and affordable, but without the range or charging speed Tesla's claiming with aluminum ion. CATL, China's battery giant, which supplies batteries to Tesla and dozens of other automakers, is investing heavily in sodium-ion and solid-state technology. They are not standing still. But compared with what Tesla is describing for aluminum-ion, CATL's technologies still have not broken through the 10-minute charging barrier or fully overcome long-term battery degradation. European automakers, Volkswagen with PowerCo, BMW, and Mercedes are pouring money into solid-state batteries through joint ventures and mergers and acquisitions. But solid-state is still held back by the challenge of mass production. QuantumScape, the solid-state startup backed by Volkswagen, still has not produced a passenger vehicle battery with enough lifespan at a reasonable cost. Japan, through Toyota, is betting heavily on both hydrogen and solid-state at the same time. Toyota has promised solid-state batteries by 2027 to 2028, but this is not the first time they have set a timeline and pushed it back. And what about traditional American automakers? GM is working with Samsung SDI on solid-state batteries. Ford is restructuring its electric vehicle division after years of losses. Stellantis is still looking for a clear path forward. Overall, Tesla currently has no public competitor pursuing aluminum ion at the same level. That could be an advantage, or it could also be a warning sign that the technical difficulty of this path is so high that the rest of the industry has chosen to ignore it. Still, if Tesla can prove that aluminum ion not only works in the lab but can also be produced for under $40 per kilowatt hour, then every competitor will have to redirect its strategy within months, because at that price, no one can compete economically. So, in the end, the biggest question remains, is this technology truly powerful enough to change the future, and how far could its impact spread? If this is real, how would the world change? Let's set skepticism aside for a few minutes and really think about the impact if what Tesla is describing about aluminum-ion batteries actually becomes real at mass production scale. For American consumers, especially people between 45 and 65 years old, the generation that is used to gasoline cars, worries about charging time, and doubts battery durability, this would be a shift that crosses the psychological barrier. Not because the technology is 10 or 20% better, but because the three biggest obstacles would disappear at once: long charging times, limited driving range, and fear that the battery will fail after a few years. When an electric vehicle can charge in the same amount of time it takes you to grab coffee at a rest stop, travel farther than almost any road trip on a single charge, and keep its battery from degrading for 25 years, the whole debate over whether people should switch to electric vehicles starts to lose meaning. The question is no longer, should I buy an electric vehicle? The question becomes, why would I still buy a gasoline car? For the energy industry, the impact is even bigger. Tesla describes each aluminum-ion battery pack in the Model 2 as being able to deliver up to 2 megawatts of instant power, enough to power 200 homes. With vehicle-to-grid or V-to-G bidirectional charging technology, every Tesla parked in a garage becomes a mobile energy storage unit. Multiply that by millions of cars nationwide, and you have a massive distributed electricity storage network capable of stabilizing the national grid during peak hours without building a single new power plant. That is not just theory. Texas experienced catastrophic grid failures during the winter of 2021. California regularly faces electricity shortages during the summer. A network of millions of Teslas that can sell power back to the grid during those hours would not just solve an energy problem, it could also create passive income for vehicle owners. For the global supply chain, the geopolitical impact can be measured even before aluminum ion reaches full mass production. China currently controls more than 80% of global lithium refining capacity, a massive geopolitical lever in a world becoming increasingly dependent on electric vehicles. If Tesla can truly separate the battery supply chain from lithium and cobalt, that would be a strategic shift at the national level, not just the corporate level. For traditional automakers, especially Detroit's big three GM, Ford, and Stellantis, this is the worst-case scenario their leadership teams have feared for years. If an electric vehicle can sell for under $16,000 while offering superior performance, then the entire compact and mainstream sedan segment, the backbone of their revenue, would be seriously threatened. Not in 10 years, possibly in 3 to 5 years, if Tesla can deliver on its production promise. And for gas stations, repair shops, and the entire gasoline car service ecosystem, this would be an obituary written in technical ink, not emotional ink. Electric vehicles have far fewer moving parts than gasoline cars, no oil filters, no spark plugs, no complicated transmission. Maintenance costs move close to zero. With a battery that does not degrade for 25 years, even battery replacement is no longer a constant concern. We may be standing in front of an economic structure that could be completely reshaped, not by a crisis and not by government law, but by a battery. Let's look back at everything we just went through. For decades, the electric vehicle industry has been built on one assumption: the future is lithium, and our job is to make lithium a little better over time. Every $1 billion invested, every national strategy, every business model, all of it has been built on that foundation. If Tesla has truly figured out how to turn aluminum ion from theory into production reality, then this is not just a technical step forward. It is a rejection of that entire foundation. And industrial history shows us one thing: when a foundation is rejected, everything built on top of it can collapse faster than people expect. But we also need to be honest with each other. This is still not a fully verified fact. The numbers we discussed today come from internal sources, private events, and reports that have not been independently confirmed. Tesla could absolutely run into production barriers that push the real timeline much further out than what is being presented. That is the truth any honest analyst has to admit. So the biggest question we need to ask is not, can this technology work? The real question is, can Tesla bring it to the mass market at the promised cost, within the promised timeline, and at a scale big enough to change the game? That is the question the next few years will answer. And no matter what the answer turns out to be, the race has already started, and it will not go back to the way it was. What do you think? Do you believe Tesla's aluminum-ion battery is a real revolution, or are we watching the familiar cycle of huge promises and real-world delays happen all over again? Leave your thoughts in the comments below. I read every comment, and I genuinely want to hear your point of view. If this video gave you a new perspective, hit like and subscribe so you do not miss the next deep dives into electric vehicle technology, energy, and the quiet revolutions reshaping the world. I will see you in the next video.